Okay. So the nodal method assignment is due on Wednesday. And then also on Wednesday, we're going to have our first quiz of the semester. And before you start getting too stressed out about that, I'll just remind you that all of the quizzes we have this semester combined only account for 3% of your grade. So actually, a quiz is worth less than a homework assignment. So hopefully that'll take the edge off. Really, the purpose of the quiz is for you to get some experience seeing what questions are like that I write. So it's mainly just as a check of whether you understand certain things in the course up till now and kind of laying the groundwork for a successful midterm exam, because that'll be coming up in a little while. So we'll have that quiz. It'll only take about 10 minutes at the beginning of class on Wednesday. So definitely be sure to be on time for that one. Today we're going to continue with the Hardy-Cross method. We did a relatively simple example in class on Friday when I kept you a minute late, and I'm going to let you out 2 minutes early today. So that's a pretty good rate of return if you think about it. You know, you can't go to the bank and get that kind of rate of return. So anyways. All right, so any questions about this previous example? I mean, it's so easy to forget a minus sign here or click on the wrong cell there. I mean, I absolutely get that one false move and the whole method falls apart. But that aside, are there any conceptual questions or any confusion in the procedure that I could address before we start working on this slightly more complicated example? I did have a few people stop by after class last time to look at their spreadsheets, and that's just like a gift that sent me into the weekend in a good mood. I love looking at spreadsheets, and so if you need help on these, stop by. You'll be doing me a favor and you'll be doing yourself a favor, all right? I really love this Hardy-Cross method. So what we're going to do with this next example is instead of having just a fixed R value, which isn't really realistic, because what we know is that the friction depends on the flow rate through each pipe. So we're going to take things up to the next level of sophistication and reality. And the main principle here to begin is with the flow balance. And so let me give you a handout that shows the network. On the handout, which I'll be giving you in just a minute, it has the network, the inflows, the outflows, and so you're going to be doing that thing where you write the arrow and the flow magnitude, just making sure that each junction, the continuity is honored. And then in the template file that's available right now on Blackboard, the second tab at the bottom has these column headings. And so the procedure's the same, but there's just a couple of intermediate things that we're adding in to the spreadsheet so that we can calculate an updated F value. Since we don't know initial F values, because we don't know the flow rates in our first iteration, we're going to do better than just the initial guess out of thin air. We're going to use the fully turbulent flow assumption for our first guess values of F, but then in the second and subsequent iterations, we'll switch over to the full Jane equation. And then once our solution is converged, meaning that the F values aren't changing anymore, that the flow rates have stabilized from one iteration to another, when things aren't changing any longer and the solution is finished, then we're going to calculate the head loss through each pipe and therefore the pressure at each junction. Because in this network, we know the pressure at junction A is 600 kilopascals. So that would be a measured pressure, or it could be that there's a reservoir of some sort that is connected to that junction that defines the pressure. And so if we know the pressure at one location and we know the flow rate through each of the pipes, then we can calculate the pressure at each of the other junctions as well. Okay, so as you get the handout, first thing that you should do is just the flow rates, your initial guess flow rates. I'll show you in a minute what I've had for mine, but yours don't have to match mine for this to eventually converge. And so we want to know how much flow is going through each of the pipes. But the initial guess, we simply start with either a flow going in or a flow going out at one of the junctions. And as long as the flow is balanced at that junction, and then you go to the next junction in the line, you just make it so that the flow rates balance the inflow and the outflow at each of those locations that's labeled with a letter. So I'll pause for a moment and give you some time to do that, and I recommend you have someone double check and have the person you're sitting next to look over your shoulder, make sure that you haven't missed something on your initial flow balance. Wednesday, if I just had you do a flow balance, you know, the initial guess flow balance, it won't be that, but it could be. Okay, so here is my initial flow guess. I went the boring route. You can see here at junction A, if I've got one coming in, I said, well, I'll send half of it down to F, half of it over to B. And so if I've got 0.5 going into B and 0.6 going out, then that tells me I have to go from C towards B with 0.1. And then if at, let's see, where am I at here? Junction E has 1.6 going out, so that means that I have to have 1.6 coming in. And so the same thing I could say at junction D. If I look at the flow of 1.2 coming in, what I did was I just split that into half up towards C, half over towards F. So at junction C, since I know that there's 0.1 going out and 0.6 going into C, then that is what defines CE as being 0.5. And so then if 0.5 is going into E from C and 1.6 is coming out, then the last thing I did in this flow balance was the 1.1 from F to E. So it looks like what I did was I split the inflows half and half at each inflow location, and then I kind of just started to let the chips fall wherever they may after that. You know, if I had half cubic meter per second coming down towards F and 0.6 cubic meters per second coming to F from D, then that forces it to be 1.1 towards E, because there's no other outflow here at location F. So you'll get better at this as you do more of them. If it's not immediately obvious to you when you sit down and start working on it, that's okay. All right, so what I'm going to do is open up this template file down here, example 2 tab, and I have my initial flow rates, and it's probably on your spreadsheet as well, but you can go with your initial flow rates. You don't have to use mine necessarily, but what you will have to do is follow the same process. And so we're just going to label this as iteration 1. And by the way, we're doing the same procedure of labeling the loops. So here I've labeled the upper loop as loop 1, the lower loop is loop 2, and then the flow direction is going to indicate whether I've got a positive or a negative flow rate as I enter in the cues. Okay, so iteration 1, loop 1. The pipes that are in loop 1 is pipe AB, BC, CE, EF, and AF. Those are all of the pipes that are in loop 1. Now, who can remember, like within loop 1, there's 2 pipes that have special significance, which I'm going to want to bold. Do you remember which 2 pipes are the ones that we really have to pay close attention to because they're special in some way? CE and EF, that's right. So what makes those so important? Why do I want to bold CE and EF so that I remember that they're somehow different. What's the catch with those? They're shared between loop 1 and loop 2, so then what about the procedure? How is that going to change my procedure?
The signs flip.
The signs flip. So I'm going to use a minus sign when I refer to the updating of the flow rate. So I'll show you that when we come to it, but that's why I'm bolding it here, is just as a reminder to myself that those are the common pipes, the pipes that are in both loops. Okay, so the example said that the K sub S, the equivalent sand roughness for each of these, I think it said it's 0.3 millimeters for all pipes. We're just assuming it's made out of the same stuff. So 0.3 divided by 1,000, so 0.0003. And I'll just drag that down so that it applies to all of the pipes within loop 1. Now I need to type in the diameter for each of these pipes. Now remember, this starts off slow. It's kind of tedious when I'm having to type all these values in during the first iteration, but after we set up the first iteration, we can copy most of it, and after the second iteration, we can copy everything. So although this process begins a little bit slow, things pick up. So 0.5 is the diameter for pipe AB. 0.65 is BC. 0.6 is the diameter of CE. EF has a diameter of 0.7 meters. And AF has a diameter of 0.4 meters. Okay, let's now calculate the cross-sectional area for each of these pipes. So I'm going to type in a formula starting with the equal sign. Pi, P-I, open and close parentheses, pi times the diameter. So I'm just going to click on the diameter cell location and square it. So raised to the 2 power divided by 4. Okay, so that gives me the diameter of 0.1963, for example, for pipe AB. And I can drag that formula down and it'll calculate the diameter for each of the other pipes in loop 1. Now I just need to key in the length of each of these pipes. So for instance, it's 220 meters for pipe AB, 100 for pipe BC, 150 is the length of pipe CE, EF has a length of 80 meters, and AF has a length of 180. Okay? Since I'm in this preliminary mode, I'm going to go ahead and do it for loop 2 as well before getting into the calculation. So put an extra line in, and then let's put in all the preliminary data for loop 2. We need this blank line because we're going to do the sums. So we need one row to do that. So there's going to be, in loop 2, CD, CE, EF, and DF. Now I'm going to bold the 2 pipes that are special, CE and EF, as a reminder to myself. And now let me just put in the equivalent sand roughness for those pipes. And the diameter is 0.85 for pipe CD, 0.6 for CE, 0.7 for EF, and DF has a diameter of 0.5. And now I don't have to type that formula in again. I can just copy it down. So I'll do that. Push the copy button. Down here I'll do the paste button. And it calculates the diameter for the area for whatever diameter is in this row. And I can drag the formula down, and it'll apply it to the other diameters as well. Now I need to type in the pipe lengths. So CD has a length of 80, CE is 150, EF is 80, and DF is 200. All right, so any questions or problems so far? Okay, initially we are assuming fully turbulent flow. So here's the full Jane equation. Fully turbulent flow says we don't know the flow rate yet. We don't know the flow velocity. Let's just assume it's really big so that this second term here cancels out. So I'm going to write this function for the F values as just 1.325 divided by parentheses logarithm of k sub s. So here is k sub s divided by 3.7 divided by d. And I'm going to briefly pause and make sure that the k sub s and the d are in the same units. Because if they're not, then I'm going to have to make a correction. But in this case, I've already put the equivalent sand roughness in terms of meters and the diameters in meters, and so I'm good here. I can close that parentheses, and then I want to square the denominator. Okay. So I've got my initial guess of the F value if conditions are fully turbulent, and I can drag that down for all of the pipes. And now R. Okay, R value, here you can see the formula for R value. It's the friction coefficient times the length in the numerator, and denominator 2GA squared times D. So I have cells I can click on for each of those. So this formula should be relatively easy to come up with. It is just F times L divided by parentheses 2 times 9.81 for G times, here is A, and I'll raise that to the power of 2 times D. All right. So my formula for R, so that R is resistance, and it's just the coefficient that goes in front of the flow rate squared when I'm calculating the head loss. Okay, so 10.12 is going to be the initial guess of resistance for pipe AB, and I can drag this down for all of the pipes within iteration 1. Okay, N is the exponent coefficient that is determined whether you're using the Hazen-Williams friction loss method or the Darcy-Weisbach, and we're going all the way maximum accuracy, maximum sophistication. So the coefficient is 2 if you're using the Darcy-Weisbach equation, because in the Darcy-Weisbach equation, head loss is related to the flow rate squared. So that's why the coefficient is 2. It's going to be 2 for all of them. Okay. Now this is where we're going to have to be cautious, because we need to get the sign correct for these initial flow rates. Now you can go with mine if you want. The advantage of using my flow rates is that then you'll know if you've got a mistake, because your numbers on your spreadsheet will look different than mine if you've typed something in wrong. But if you want to use your flow rates, that's fine too. We can correct any spreadsheet errors if and when they pop up. So let me just zoom in a little bit here. Okay, so the flow rate for pipe AB is going to be 0.5. That's positive clockwise flow direction, so we leave it in the positive sign here. Okay, pipe BC is negative 0.1. Let me just, every time I scroll, it doesn't show up that good. Okay, so negative 0.1 because it's opposite to clockwise, so minus 0.1. Okay, this next row is for CE, which is positive 0.5, because CE, when we look at it from the perspective of loop 1, is in the clockwise direction. So 0.5. Now, next is pipe EF, which you can see that's against the clockwise within the perspective of loop 1, so negative 1.1. And then negative 0.5 is the flow rate for AF. So negative 0.5. Now I'm not going to go all the way, and I'm not going to type in the flow rates yet for loop 2, because 2 of those flow rates are going to depend on what I calculate within loop 1. So I'll just wait to fill in this stuff until later. So instead, I'm going to begin calculating these terms, which I need to find the correction factor. So R times Q times the absolute value of Q, so ABS parentheses, I'll just type in K19 here, okay. So R times Q times absolute value of Q, and if you drag that down, you'll notice that the flow rates that were negative ends up with this term is still negative because we've got the flow rate times the absolute value of the flow rate. So that directionality or the sign is preserved. Same thing with this next column where we had N times R times the absolute value of Q okay. And now beneath we need to calculate the sum of those, because remember that our correction factor, in your handout you've got the formula for our correction factor. Here it is. This is our correction factor. It's the negative of the sign, the sum of R times Q times absolute value of Q divided by the sum of N times R times absolute value of Q. So that's why we need to add these all up, is that we want to have the sum of each. So the sum of those ones, and then I can drag that sideways and it will find the sum of the next column as well. So the sum of one and the sum of the other. And now my delta Q is going to be equals minus 1 divided by the other. And I'm not anchoring that reference. I'm going to type the formula in manually over and over because I want to be able to copy and paste for my next iteration and not have the formula always looking within the first iteration. So I want it to be a relative reference rather than an absolute reference. That's why I'm typing the formula in rather than like anchoring it with the dollar signs. So equals minus 1 divided by the other equals minus 1 divided by the other. Okay. Now, the corrected flow rate is our initial guess plus the delta Q. So corrected flow rate equals our initial guess of flow rate plus delta Q. All right. And assuming that we've set everything up correctly, the delta Q for the next iteration should be lower than the delta Q of the first iteration. If your delta Q ever increases, that means you've got a mistake. So that can be an indicator that something's not set up right, whether it's a flow balance at the junctions issue or maybe a spreadsheet calculation mistake. But the delta Q should always be getting smaller. Okay, now let's find the absolute value of the velocity through each pipe. And we're going to use that to calculate the Reynolds number. So that's why I want to know the absolute value of the velocity. So V is Q divided by A. So I'm going to say equals absolute value of Q divided by A. So that's going to give me the velocity of the flow through the pipe for each of the pipes. And then Reynolds number is going to be the velocity times the diameter divided by the kinematic viscosity of water. And since we're in traditional units, that's just 1 times 10 to the minus 6th meters squared per second. So I'm going to write 1e minus 6. That's 10 to the minus 6th power. Okay, so we've got a Reynolds number for each pipe. And we're going to use this Reynolds number when we calculate an updated F value later on in the next iteration. But then this percent change column will be useful for us to see how much the flow rate is changing within each iteration. So we're going to have the updated flow rate minus the initial flow rate divided by the updated flow rate times 100 for this percent change. And so the percent change is parentheses corrected minus our initial guess divided by the corrected flow rate times 100. That's just showing us like what percent change in flow rate occurred within the calculations of that iteration for each pipe in question. So for instance, 17% increase in flow rate for pipe AB, 26% decrease in flow rate for pipe AF. Now pipe BC is going to be a tricky one. The hard pipes are the ones that have really low flow rates. They're the ones where you're going to have multiple iterations to finally get equilibrium. So you notice that huge percent change. Hopefully it'll settle down over subsequent iterations, but most likely pipe BC is going to be the one that converges last, at least based on my initial flow balance. Now, if you went with your own flow balance, then all of these numbers are going to be different, and that's fine. No need to panic. Okay, so let's go to the flow rates now, unless there's any questions so far. Go ahead.
What was that formula again?
For the percent change?
Yes. Might be about right.
Okay, it is, you need to have equals and then parentheses. It's the corrected flow rate minus the initial flow rate and then close parentheses divided by the corrected flow rate times 100. Good. All right. Other questions? Okay, so back to the flow rate. So CD, now remember, we're in loop 2 now. So think about what is the clockwise direction within the perspective of loop 2. Okay, so CD is going to be minus 0.6. Okay, CE, now this is the one that's in bold. To remind me, I shouldn't use my initial guess for CE. I can do better than that. CE should be equals minus of my earlier, the flow rate that I just barely calculated within the perspective of loop 1. So equals minus the corrected flow rate in the previous loop. So I put that minus sign because pipe CE was a positive flow rate when I was looking at pipe CE from loop 1, but now in loop 2, that's anti-clockwise, and so it's a minus. So, okay, we've got our initial guess for CE. Same thing with EF. I'm going to have equals minus my previous guess of EF. And then for pipe DF, I'll just put in my initial guess, because I don't have any better flow rate estimate for it than my initial guess of 0.6. And that was positive because it was clockwise. Okay, now I can just copy both of these formulas. I need 4 of them, so I'm going to copy 4 of those formulas down here and paste. And so it will look in the right spot for each row. Yep. So I copied 4 of them because I had 4 rows that I wanted. I could have just copied one and then dragged it down. Okay, I need to sum things up, so equals sum of these cells above, and I like to italicize that. I drag it to the side, and it will calculate the sum of the cells above. And now this tedious thing of typing in the correction factor formula, I guess I ought to just paste it for completeness into my spreadsheet. So this is the formula that I'm typing in right now, this delta Q. So it's equals minus 1 divided by the other. So don't forget the minus sign. Okay. So with the delta Q, I can now add the initial flow rate to the correction. So we combine them together and get the updated corrected flow rate. Okay, and then I want to get the velocity, so I can just copy the formula where I had velocity before. I'll copy 4 of them, Control C, paste with Control V. It calculates the velocity for each pipe. Same thing with percent change and Reynolds number. I could do both of those at the same time. Control C and paste. When I paste, it knows to paste the formulas. It doesn't paste the number. It pastes what's in those cells, which is equations. So as I paste, it's calculating the Reynolds number and the percent change in the flow rate. Okay, we're done with iteration 1. And our flow guesses are better than they were initially, but we still got a long ways to go because I like to see a flow rate percent change of less than 1%. And we haven't achieved that for any of our pipes. And remember that what's going on in the background, the whole kind of theoretical underpinning of this method, is it's looking for what flow rate makes it so that, regardless of route, you have the same head loss from one point to the other. So think about if you go from junction A to junction E. You could get there A, F, E. Or you could get there A, B, C, E. So through either of those routes, there should be the same head loss going from one junction to the other. So that's what's going on in the background. And these little series of corrections are intended to make it so that we have the same head loss. Now, iteration 2. We can copy all of this through the length because none of that is going to change. So Control C to copy and give it one gap row so we don't accidentally overwrite our sums. And paste, and all we have to do is change the label where it says iteration 1, it's actually now iteration 2. Okay, so all of that is the same. Those are constants. But we're changing our F values. We used fully turbulent flow assumption in our first iteration, but now that we have flow rates and Reynolds numbers, we're going to use those Reynolds numbers to calculate updated F values. Okay, so my new guess F value here is going to be equals 1.325 divided by the logarithm, parentheses, now K sub S divided by 3.7 divided by D. So that's one of the terms. Now plus 5.74 divided by the Reynolds number in the previous iteration, this Reynolds number, to the power of 0.9. I'll close parentheses, so that closes out the logarithm, and then another close parentheses gives me the opportunity to take it to the power of 2. Okay, so it's k sub s divided by 3.7 divided by d. Then the plus means that we're starting the second term here, numerator of the second term, 5.74 divided by the Reynolds number to the 0.9 power. All right, so let's see, how does my f value change? Not too different from the first guess. The first guess had it as 1.74. I'm not sure why the font changed suddenly in that location. We were at 11 point before. I'll change that back. Okay, so I can drag that down for all of them. The common pipe, CE, you'll notice that there's a slightly different F value. I'm not going to get hung up on that really slight difference. It will vanish in subsequent iterations. Already here in the second iteration, it's more or less converged, the F value has. Okay, so now for the R values, I can just calculate, I can grab this whole column of data, Control C, and paste that down, and it's going to calculate new R values based on this improved estimate of F that we've got. And N is 2 for each of the pipes. Okay. Now, we're about to do the last part where we're kind of interacting in a substantial way rather than just copy-paste. We have to make sure that we have the updated flow rate. So this is a mistake I sometimes see people just put in their initial guess again. Like if you just put in 0.5 here again, then that would be a real lost opportunity, because we know a better guess of what the flow rate is there in pipe AB. So have it equals of this corrected Q from the previous iteration. Okay, same thing with BC. Where's our best guess of BC? It's there. Okay, CE, I'm going to do equals minus and use this loop 2 guess of CE. Same thing for EF, equals minus the most recent version of EF I have was in loop 2, so I have to use the minus sign to flip the flow direction. And then AF was just iteration 1, loop 1, updated corrected Q for AF. Click on that cell location. All right. Now that I've done that, I can copy all of the rest of the calculations for iteration from iteration 1. So this entire block of calculations I can copy and then paste below it, and it's going to do everything I need. And what we see is the percent change is much lower than it was in the previous iteration. The delta Q is getting smaller. It went from 0.1 to 0.02. So things are headed in the right direction. Okay, now I'm going to do the flow rates again here. So CD, it's equals the corrected flow rate from iteration 1, loop 2 for CD. But then CE, where's my best, freshest estimate of the flow rate through pipe CE? Well, it's in the calculations I just barely did for loop 1. So equals minus this one equals minus that one, and then DF is the corrected Q here. All right. So now with that done, I can grab the formula for all of the rest of the columns for loop 2 and copy it. Control C, paste it, Control V. All right, things are again headed in the right direction. My percent change is getting smaller. The correction factor is getting smaller. And now things really get easy from here. I'm zooming out a little bit because I don't really need to see the numbers so much anymore. Now I'm just selecting big blocks of text. So now I'm going to select the entire iteration, all of it. And I'm going to copy and paste it immediately below, down here, paste. And the only thing I need to do is just change the label. It's not iteration 2, it's iteration 3. But if you look, it did all the updates, like it went and got the most recent flow rate from iteration 2. It's doing the most recent flow rate for any one of these pipes, and the percent change is getting smaller. We're below 1% for everything except for pipe BC, which is a tricky pipe because the flow rate is so low. There's almost no flow going through that pipe, and so the F value is difficult to calculate. But we can just copy and paste again. And now we're down to about 1.2% change in iteration 4, and that's where I left it. I said, you know, if you look at the flow rate is 0.019 in iteration 4. In iteration 3, it was 0.016. We could do a fifth iteration if we wanted to, but basically things have converged. The more complicated the pipe network, the more iterations you'll have to do. See here in the fifth iteration now it's down below 1%. I'm going to delete that fifth iteration because I've got some other calculations that we're going to do real quick here. So now we know our flow rates through each pipe. And we can calculate the head loss through each pipe. I'll do that over here on the side. I'm going to have the pipe H sub F in terms of meters. And our formula for head loss, you can see down here at the bottom, it's R times Q to the power of N. So equals, here's R times Q to the power of N. And this is going to tell me the amount of head loss that occurs through each pipe. It's probably more digits of precision than I need to display. All right, so let me drag this down, and I've got the head loss through each pipe. So I know the flow rate through each pipe, the head loss through each pipe, and there was a control point at junction A. In the handout, you can see it says that the pressure there is 600 kPa. So how much head is at junction A? It is the pressure of 600 kilopascals divided by 9.81. So there's 61.162 meters of head at junction A. So how much head is there at junction B? Well, it's going to be the amount of head at junction A minus the losses through AB. So here we can see that there's 3.49 meters of head loss through pipe AB. So the head at junction B is the head at A minus the losses through A and B. All right, we're going to leave it here for today because we're out of time. So save your work, and we'll briefly pick this back up on Wednesday to calculate the head at each junction and the pressure at each junction. If I just review the announcements briefly, remember that your next homework assignment, the nodal method, that's due on Wednesday before class, and we're going to have that brief quiz at the beginning of class on Wednesday. All right, have a good one.